G'day Method students. In this video we're going to have a look at differentiability and what it means for a function to be differentiable, which is just a fancy way of saying able to be differentiated at a particular point. Again, like the last section on limits and continuity, it's a little bit wordy. There's some definitions to try to understand, but we do thankfully kind of have some, I guess, formal ways and also informal ways which can be a little bit easier to apply in practice. So let's get into it. In this section, we're saying for a derivative to exist, the function must be continuous and smooth at that point. Okay, so what we mean by that is, well, firstly, if we remind ourselves of what continuous means, if we're talking about a function at a particular point where x equals a, then we must have a function being continuous at x equals a, which actually means two things. To be continuous, it means that f of a is defined. Right, which makes sense. You have to actually have a point on your graph at x equals a. And it also means that the limit of f of x, I haven't given myself enough space here, as x approaches a exists. Which from the last video you might remember means that as we approach from the left-hand side and from the right-hand side, we have to be approaching the same thing. Okay, so the lines have got to be meeting up when x is equal to a. We can't have a jump or a big gap or an asymptote or something like that. So 1, f of a must be defined. 2, the limit as x approaches a must exist. And 3, the gradient also has to approach the same value from the left and from the right. So we're using this word smooth, which just means we can't have like a jagged, sharp corner. But really all that means is that as you're coming from the left-hand side and from the right-hand side, the gradient must be approaching the same value at the point that you're investigating, okay? Like with continuity, sometimes it's good to know where a function is not differentiable, because that can help you identify where it is differentiable. So anytime we have holes or breaks, like just gaps in the graph, then not differentiable, we can't work out the gradient. Any sharp corners, we can't work out the gradient. And the endpoints of a domain, any endpoints, you actually can't work out the gradient. We say it's not differentiable. Another way to think of this, and it hasn't been written on the notes here, is that to be differentiable, you need to be able to draw a tangent line. Must be able to draw a tangent. Okay, so if you have a point on the graph anywhere where for some reason you couldn't draw a tangent line, then at that point it's not differentiable. So let's get into some examples and hopefully they'll make sense as we go through them. For example 29, it says to state the values of x for which the function shown is differentiable. Now I've got a hybrid function here. And if we're looking at where it is differentiable, well this sort of linear section of the graph over on the left-hand side here, all of those values along there would be differentiable, right? We could work out the gradient at any of these points, no problem. When we get to the point where x equals -2, this is a sharp corner. This is going to be a point that's not differentiable. One way you can sort of think of why this isn't differentiable is that if you tried to draw a tangent line at x equals -2, you wouldn't really know where to draw the tangent line and what direction to give it, right? Because do you use the gradient as it's coming from the left-hand side, or do you use the gradient as it's coming from the right-hand side, or do you use a different thing, right? Like I could sort of imagine drawing lots of possible tangent lines here, but there's not one defined tangent line that is the gradient at x equals -2. So the function is differentiable for x is an element of, we said -∞ up to -2, no problem. It's just when we hit -2 where it's not differentiable. So that's why that's got a round bracket around -2 there. As we said, the reason it's not differentiable here is that the gradient as we come from the left-hand side is different to the gradient as we come from the right-hand side. And that's our more technical way of knowing that it's not differentiable. Okay, then we get this sort of like parabola-looking part of our graph, where that must be the rule for this section of the domain. And for all these points, we've got a continuous smooth line, no problem. We could draw tangent lines at all these points. We could work out the gradient at all these points if we had the equation. Again, until we get to this end point here, right? Now this open circle, this is not differentiable for a couple of reasons. One, because it's not defined, because that's an open circle, so we know straight away that it's not differentiable at x equals 1, but it's also an endpoint. So even if that was a closed circle, if you were trying to draw a tangent line at that endpoint, you kind of wouldn't know where to draw your tangent line. It's almost like your tangent line would sort of drop off a cliff here. You could have that way, or you know, who knows. So it's differentiable from -2 all the way to 1, but not at either of those endpoints. So we use the union symbol here, -2 to 1, but neither of those are included. And then we've got a gap in the graph. So between x's 1 and 2, you can't differentiate it. There's no graph that exists to even find a gradient of. From 2 onwards, we're fine, right? We've got a linear section of the graph again, and we can work out the gradient in any of those points. So it is differentiable. The endpoint, though, again, is not included. We can't differentiate at the endpoint of a domain. Again, because if you were trying to use a ruler here, right? If I was drawing a tangent line, you know, somewhere along the graph here, well, I know where the gradient is, except when I'm at this endpoint, in theory, I could draw a tangent line that does anything like this. That's sort of a weird way of thinking of it, but really, I wouldn't know where to draw the tangent line at that endpoint. Or I guess another way of thinking of it is, can I work out the gradient from both directions? Well, I can certainly work out the gradient as I'm coming from the right, but I can't work out the gradient as I'm coming from the left because there's no graph here. So at the point x equals 2, it's not differentiable. So we're going to say from 2 to infinity, it is differentiable, but not including 2. Okay. Okay. Example 30 gives us another hybrid function, and this is a linear graph. Now, this graph is actually continuous all the way through its domain, right? Even at this point x equals 3, where we have this kind of sharp corner, it's continuous. I can draw this graph without lifting my pen off the paper, but it's asking us to explain why the function shown is not differentiable at the point 3, 1. So why at this point here is the function not differentiable? And it's not differentiable because the gradient as we're coming from the left-hand side, which looks like it's +1, is different to the gradient as we're coming from the right-hand side, right? Because the gradient as we're coming from the right-hand side is -1. For it to be differentiable, it would need to be a smooth join. This would need to be like a curve rather than this sharp corner, okay? And that's the reason that it's not differentiable. How can we write that or say that using words or notation? Well, what we're trying to say is that the gradient, let's say, gradient as x approaches 3 from the negative direction does not equal gradient as x approaches 3 from the positive direction. Okay, the informal way was like that sharp corner thing, right? We said we can't, it's not differentiable where you have a sharp corner. We've just said that, I guess, in slightly more technical language there. So I hope that gives you an idea of differentiability. Again, sometimes when you're answering the questions, the answers seem relatively straightforward, but it's understanding all the definitions and meanings and stuff like that along the way that can be tricky. So read questions carefully. When you're checking answers, read the answers carefully. And as always, ask your teachers for help if you need a bit of extra support. Cheers.